Hello everyone. Today I'm going to run through some electric VLSI exercises. Before doing this, we need to make sure our software has the right setting. First of all, we need to bring up the Electric VLSI window. I just double click on the Java image electric binary. Now I have the Electric VLSI window. The very first thing you need to do before doing any design is to make sure the setting is correct, the configuration is correct. Different technology will require different settings. To set the first settings, we need to go to choose preference, which is under the file tabs, and then go to the select the technology menu, and then we go to the technology project preference. For the startup technologies, I would choose schematic. For the layout technologies, I would choose MOMOS. And this option have to be checked for almost all the CMOS technologies. Almost all the CMOS technologies is based on the P-substrate. So we have checked out the option P-substrate processed in the layout technologies. Now metal layers, we select 2 metal layers. This means that when you connect it from one device terminal to another, we need only 2 metals. And you can also use polysilicon to connect the device terminal. In this case, you need polysilicon. For our application, we need to check this box, second polysilicon layer. Also, we need to select standard CMOS rules, which is applicable for almost all the CMOS technologies with less than 4 metal layers. We don't allow any stack vias. So we check this box. And of course, we are going to deal with analog design. Now scales. We need to make sure we are in MOMOS or most CMOS. And now the scale is 300, right? This will depend on the foundry parameters. We just assume that this 300 is okay for us. Okay, apply okay. Now, another thing we need to define in our configuration is the SPICE. So we go to the tools preference, and we go into the SPICE CDL preference, SPICE CDL user preference. This is the window for defining the parameter for the SPICE simulators. In our case, we use LTSpice as the SPICE engine. There is no option for LTSpice, but the actual simulator we are going to use is LTSpice. The SPICE level will be number 3. Now, here, after writing the text, right, we ignore the output. So this is the option we are going to do. You should not pick don't run. You have to run the software. And run program. The run program will be the LTSpice executable. The full path of the LTSpice executable. In my case, is d:\program files LTSpice XVI / and then xvLLX64.exe. And also you need the arguments, right? You need -i and then $file name and -r $file name no exe. I have already included this command in the natural looks. And obviously you need to define the run directory. You need to check this box, use dir, use directory. And here I have already created directory called VLSI in the desktop. You can create another directory in other places. It's up to you. And then all you need is to put the full path of your simulation run directory in here. And finally, you need to override the existing output files, so you can rerun the simulator again and again. Now you have already got the configuration for SPICE simulator. The next thing you are going to do is to click on the DRC option, and where you can define the DRC user preference. You need to check multi-thread DRC. This option is very important. And then you click apply, OK. Now, basically, you have already got all the preference, all the important preference done. And perhaps you also need to look into the NCC preference. NCC stands for Network Consistency Check. Yeah, we are going to use hierarchical comparison. NCC checks will allow you to compare the connectivity of your schematic and the layout. Here we are going to use hierarchical. And other than that, perhaps we don't need to compare the transistor size, but you can check this box anyway. So everything should be okay. Yeah, all set. Now to begin with, you need to go to the Explorer menu. You don't in your first design, you need to create a library. For instance, in my case, I'm going to create a library called EIT. So we name this library EIT. And then I'm going to create a cell using the create new cell option. And to start with, I'm going to create a voltage divider, R D divider. Now you have the schematic. You have the cell created, R divider. And this is the schematic window. And then the first thing that I will do is to create a schematic for this voltage divider. First of all, just like any other divider, you have two transistors at least, two resistors at least. And in VLSI, you can use N-well to develop the resistor. Now the resistor value is 10K. And the width is 50, and the length is 150. So this is the first resistor. And we need three of them. And I rotate this. And I copy another one. Now you have three resistors. They are all the same, identical. Now, to connect the wire, you left click on the component and then position your cursor very close to one of the terminals of the device you want to connect, and then press the right button of your mouse. Do not release the right button, and then move the right button, drag it across to the wire to create the wire. Then the wire will be created to the place where you drag to, and then you create another one. So I got the wire connected for this, and I'm going to do the same for here, and I'm going to do the same for here, and I'm going to do the same for here, and I'm going to do the same for here. Now you need to connect the pins to the voltage divider. Cannot be lazy. And then I create the last pin. Left click on the component and then right click to draw the wire. Press the right button to draw the wire. Now you have already created a design, and then I'm going to save this. Now you want to create the pins. This one will be V in, and this one will be V out, and this one will be ground. And the last thing you are going to do is to clean up the pins everywhere. This step is important. Now you have got the design. The next thing we are going to do is to check whether there's any design rule violation. So I've got two errors here. Let's check what error I've got here. I need to press the shift and then the greater than angle. So what is the error? So the wire is not connected. So I need to reconnect the wire. Now I originally have two design rule violations. Now check whether, let's check. Now zero warning, zero errors. So the schematic is done. The next thing you are going to do is to do the actual layout. Now you have already got a R underscore divider. You are going to create another cell in the same library. It's also called R divider, but now it's not schematic but layout. Now under the same cells you have two views, two representation, schematic and layout. Now I've got the layout menu under the component tabs. As I already said in the beginning, we need the MOMOS technology, CMOS technologies. Now I'm going to pick an annual resistor. The annual resistor have some object properties, right? In my memory serves me well, the yield resistance is 10K. The width is 50. The length is 150. Okay. So this is the resistor I have got. I need 3 of them. Now I need to connect them. Use metal to connect the device. First of all, we need to click on metal 1 and then left click on the device which you want to begin with. I should say left click on the pins on the device which you want to start with, and then press the right button of your mouse and drag the wire across. Now I have connected 2 resistors together. Now I'm going to connect another one. So I have 2 metal connected, and then the metal may be too thin. I need to increase the width of the metal to 10 or even 40. And also, you don't want any end. You don't want any and we are going to do the same. We also want 40 as the width for the metal track, and we don't want any attachments. Now we also want another piece of metal for the ground. left click on the pin you want to start with, and then press the right button of your mouse and then drag the wire across. Now the metal width here should be also 40, and we don't want any end attachment. We also want 40. Now, yeah, okay. And we don't use any end, we will be like this, so we need end attachment, head only. Okay. Another thing we are trying to do is to check the design rule. And obviously there's no design rule error, which is a good thing. Now we are going to export, create a pin V in for this one, and then V out. V out. And then G and D. Now you have two views for your design. You have the schematic view and also the layout view. We have already done the check, the design rule check. We have no error. The next thing I'm going to do is to do a comparison between the schematic and the layout. To do that, we go to the Tools tab, and underneath the Tools tab there is an option, a pull down menu, NCC. So we are going to check the schematic layout view of the same cells. Now design rule check and network consistency check has been done. No error at all, which is a good thing. Now what else can we do? We have the schematic here. We can also do simulation on the schematic. To do that, we are going to create a SPICE files, SPICE netlist, and then go to the component tab and then select go to miscellaneous and then click here, select SPICE code. And then we are going to edit the SPICE code. Multiline. we are going to do transients analysis for 100 nanosecond. And we are going to do V in V1 and then V in 0. And what else? Let's say piecewise linear. And I forgot the way how we define the piecewise linear. You can check from the LTSpice. Just don't forget it, right? We just use DC 10 volts. Now, to simulate these circuits, we just go to the Tools tab and bring out the SPICE simulation bracket SPICE pull down menu and then write SPICE tab. Now apparently everything is okay now. I need to create another finish should be okay. And then add trace V in right 10 volts and V out 6.6 volts, which is also okay. So that's done. And I should connect this terminal to ground. Then I will do another simulation. V in correct. VO 6.6. Yeah, okay. Whatever. Now I'm going to do a simulation on the layout. Again, you can do the same thing. Go to the component tab and then select the most CMOS pull down menu, most CMOS menu, and then here you have a few options, right? You need to go to the miscellaneous option and then bring up the pull down menu, and then you have the same thing, SPICE code, where you can define the SPICE code, and you can just do the same thing. V out 1 0 and then I can also increase the text size so that it can be readable. I probably need global ground GND. And let's check whether I got it correct in here. If I do by simulation and global ground, this will tell the simulator ground is 0. Okay, done. In here I would just do the simulation straight away. Yes, there's no error. 10 volt. 6.6 volt, which is 100% consistent with the simulation result from the schematic. So this is the conclusion of the first chapter. Thank you. Bye bye.